The original.
Terry. Oh, Terry, sorry. I've never met. You know, as long as.
Okay, let's have a little look here. So click your Chromebooks all the way closed, please.
Let's go, ladies.
All right, here we go. So this is where we left off when was it? Last Thursday, last Friday. So we're evaluating functions, and we left off kind of trying to simplify an expression that involves evaluating a function, right? If we're given this function up here, f of x equals x squared plus 3x minus 4, then what if I asked you to do something like this, right? Where it's asking us to evaluate the expression f of a plus delta x minus f of a over h. Okay, that's kind of a weird thing you might think to do, but that's what we do a lot in calculus, stuff just like that. So what would we get? Well, f of a plus h, everybody agree, just works out to be that, right? Because if I just follow the rule, the function rule is this, right? It's telling us what I'm doing with input values. For every input value, I'm going to square that, and I'm going to add to that 3 times the input value, and then I'm going to subtract from that 4, right? So f of a plus h is everything in the pink box. What's f of a? Okay, good. A squared plus 3a minus 4. I'm just going to apply the function rule when the input is a. And then what am I going to do on the bottom? Divide it by h. Okay, so that's my answer, but it's not simplified. So what would I have to do to simplify this? What am I going to do? So I've got this kind of complicated looking expression. But what do you think I could do to simplify this? What are my options? Okay, so I could distribute the 3, I could distribute the negative. What about here?
Yeah, you could definitely not.
I can't distribute, but I mean I can expand it out, right? So what is that going to be? If I take a plus h squared, what is that going to become? A plus h times a plus h. Good. Okay, does anybody know what that works out to be? Plus 2ah plus h squared. Good. So if I expand that all out, that's what I get. I'm going to add to that. If I distribute the 3, I just get plus 3h, good, minus 4, right? If I distribute the negative, what do I get there?
Negative a squared plus minus 3a plus negative 3a plus 3.
Okay. Okay, so I can cancel some stuff now in algebra. When we talk about canceling vertically versus canceling horizontally, I've mentioned this before, but let's kind of revisit that idea. So if I cancel things vertically, like for example, if I had something like, let's say 6x minus 8 over 2, right? I could rewrite that as, let's make it a little easier. Let's just do, what if I had something like this? What if I had x squared minus 3x over x? If I split up that common denominator, what do I get? Okay, minus. Okay, So can I cancel some stuff?
Yes.
Yeah. I can cancel, I could reduce this fraction to
X.
x, and I could cancel vertically here, right? So if I cancel vertically, what does that become?
3.
All the Chromebooks ought to be completely closed here. So what would happen? I end up just with 3, right? So if I cancel vertically, what's the value I'm canceling to?
3.
X over x is equal to 1. Okay. So when I cancel vertically, the value that they cancel to is 1, right? That would become 3 times 1. If I cancel horizontally, though, what do they cancel to? Because you told me that, for example, you said the 4's cancel, which they do. -4 plus 4 adds to 0. Okay, so when I cancel horizontally, they go away. They go to 0, right? That's a very common mistake that people make in algebra, though, is a lot of times when they cancel things vertically. Like, what if I had another term out there, x over x? That wouldn't go to 0. That would go to 1, right? Okay, so the 4's cancel. Anything else? The a squareds cancel. Yeah.
3A.
And the 3a's cancel. What do you know? So we're only left with that term, and that term on the top, right? So let's go to, let's do this. So then I end up with, on the top, 2AH plus h squared plus 3h over h. Am I done? No. You go a little further with that. What would that be? 2a plus h plus 3. So that would be my answer. Okay. Make sense? Yeah, it's a lot of stuff. It's a lot of stuff. You'll see some things like that, in the near future. Okay, what about something like this? This is a different type of question. So now we're given a new function, h of p equals p squared plus 2p, and it says solve for h of p equals 3. So what would I be doing, Kendra?
Would you set the equation equal to 3?
Yeah, so I'm setting the function equal to 3. I'm asking the math gods here, when is the function equal to 3, right? So if we do that, we're going to set it equal to 3, and we've just got an equation now that we can solve, right? Now we can kind of shift into algebra mode and just solve this thing. What would we do to solve this equation?
The one where you divide 2 by, or what's the thing?
So we could complete the square. That's a
Yes.
possibility. Let's think about this in terms of the easiest way to do it, though. Well, where would I probably want to start with this? I mean, I always probably want to at least evaluate to see what my options are and put the quadratic equation in what form? Standard form. Good, so we'll set it equal to 0. Okay, and if I do that, what do we see? What's the easiest way to solve that one? Magic numbers, yeah. Right, we could find numbers that multiply to -3 and add to 2, +3 and -1, so that's pretty easy. Then I get my solutions, or what? I guess there they are, right? P equals -3 or P equals 1, okay? So we get 2 solutions now think what we just did, though. Think about this in terms of the discussion we had on Friday. So now we get 2 solutions where the output of the function is equal to 3, the output of the original function, right? The original function, h of p equals 3, when either p equals -3 or p equals 1, okay? What would that look like in terms of a graph, maybe? Now, when we evaluate functions, like if I go back to, like this example right there. If I just want to know where, or what's the value of the function when x equals 2? F of 2 equals, what? I don't even think we didn't even do that one, didn't even write it down. What would we get for that? yeah, f of 2 would just equal 2 squared plus 3 times 2 minus 4. So that was 6, right? 4 plus 6 is 10, minus 4 is 6. What would that look like in terms of a graph? What's that mean?
Oh, it would be like this.
So, but what is that, when we evaluate that function at 2, what's that going to give us?
1.2 times.
Okay, it's a point on the graph, right? We know there's a point on the graph of this function at x equals 2, y equals 6, right? So at the ordered pair, 2, 6, and that's just a point on the graph of the function, right? Okay, no big deal. This is a little different. What's this going to look like in terms of a graph? I mean, yeah, I guess we know that we get, well, I won't say anything. What's it look like?
2 points.
I heard someone say 2 points? Okay, what are the 2 points? So we get 1 point at,
There are 2 zeros on the x-axis.
someone said 3, negative 3?
Yo, 100.
Is that right? Is it at 3, negative 3?
I think 0.
Okay, it's not at 3, negative 3, and it's not at 0, negative 3.
3
Definitely not at 3, negative 0.
Negative 3, 0.
No. Now let's go back and think about this. Think about this from the perspective of the original question. It says, given that the function h of p equals p squared plus 2p, right? Solve for h of p equals 3. Well, what does that mean? H of p equals 3.
Y equals 3.
Ah, okay, that's the y value, isn't it, right? The function represents the output values. Remember back to algebra 1, f of x is just a fancy name for y, right? So the output of a function is giving us if we graph it on the xy plane, it would be the y value, right? So then what's an x value that goes with that y value? Negative 3. So 1 point is going to be at negative 3, 3. What's the other point going to be at? Ah, okay. At 1, 3. So what did we do? We kind of worked backwards here, didn't we? This time they gave us the output value, they gave us the y value, and we did some algebra, and we solved for the input values that give us that output value. There were more than one. Okay, so I've got a graph this time. The graph of that would represent this situation would look kind of like that,
Oh, no.
right?
Oh.
So here's our original function. This was just the function, was it h of p, is that what it was?
Yeah.
H of p equals p squared
Plus 2.
plus 2p. There it is. There's the graph of p squared plus 2p, right? Where this is the p-axis, right? Instead of x, we're using p. That's a parabola. We haven't really talked about graphs of quadratics yet, but you did a little bit of that in Algebra 1. We're going to move on to that pretty soon. But it gives us this parabolic graph. And then we wanted to know, where is the function equal to 3? Well, isn't that the same thing as just asking, where does the graph intersect a line at y equals 3? Because we asked, when does y equal 3? Well, it happens at 2 places. It happens there and there. Those just happen to be the coordinates of the places you told me, aren't they? Negative 3, 3, and positive 1, 3, right? Those are the coordinates of those places. Okay, I mean, I'm just kind of giving you a glimpse ahead a little bit. That's where we're going to be going with this stuff. We're going to look at lots of graphs of functions now. Okay? And then we're going to look for the next, week or week and a half. We're going to look at kind of not specific graphs. We're not going to really try to make specific graphs of functions. We're just going to be given some graphs of functions, and we're going to explore some properties of the graph. And then we'll kind of put everything together. We'll put together all the stuff we did with quadratics and all the stuff we're gonna soon talk about with just general graphs. And we're going to get to a point where we can take quadratic functions, as hard as we wanna make them, as complicated as a quadratic function as we wanna make it, and we can represent those with graphs. And we can do things like we could transform those graphs. We could, once we have a graph of a quadratic, we could, in exactly the way we want to, we could translate it horizontally or vertically, a specific amount. Or we could stretch it horizontally or compress, or stretch it vertically or compress it vertically, stretch it horizontally, compress it horizontally. We could reflect it over horizontal or vertical lines. We can do all that stuff in very predictable ways and exactly the way we want to with quadratic functions, and eventually with every function. Okay? So that's kind of where we're going with this stuff. This is just a little bit of a glimpse forward. Okay, and there's just a, a table. Gives us some ordered pairs, right? Values of the input, values of the output, right? We can see that these were the values we're interested in because those are the ones that have output values of 3. Okay? All right, questions? Okay, last issue. And this is kind of an honors level issue. This is, other classes aren't going to do this, but this is something you guys are going to do. This is because we're going to take one challenging example here of how do we, of evaluating functions. So what if we take the volume of a sphere? Here's the, you might remember back to geometry, this is the equation for the volume of a sphere of radius r, right? Okay, so if we graph it, it just looks like that. Okay, that's our volume function. So this, on the vertical axis, we've got V. On the horizontal axis, we've got R. You don't see it there, but there's an R. Okay, doesn't that make sense? If we're inputting values of R and we're outputting values of V, right? So for example, if we input a value of R equals 1, we're going to get an output value of 4/3 pi, okay, for the volume. Notice that the volume function increases non-linearly, right? As you go further out, as R increases more and more and more, the volume function starts to increase more rapidly. This explains the frustration you feel when you're blowing up balloons for a birthday party. The first time your first breath that you inflate the balloon, that's pretty satisfying. You get to just kind of expand real fast, right? But after a while, that balloon, when it's pretty big, each little puff you make doesn't really change it noticeably, right? How come? Well, this graph tells the whole story, doesn't it? Right. How come?
The surface area doesn't increase as fast as the volume.
Well, yeah, it tells us up here, in order to make the volume go up, in order to make the radius increase just a little bit here, look what has to happen. The volume has to increase a lot, right? When you're up on this part of the curve. In order to make the radius increase a little bit over here, the volume doesn't have to change very much. Right? You don't have to put in very much volume to make the radius increase down on this part of the curve. But up here, yeah, you got to put in a lot of extra volume to make that radius increase a little bit. And in calculus, we explore concepts like that in ways that are much better and more effective. Okay, so the question I've got for you, though, is now, if we've got volume as a function of radius, what if we wanted to do instead, we want to do something like, we want to take this function and we want to change it, and we want to express volume as a function of maybe surface area. What might that look like? So we want to come up with something like this. Come up with something like V of S. Okay, how could we do that? Any suggestions? Forgot what I had done, so I actually didn't have a solution. Okay. So what can we do? I guess what is the surface area of a sphere? You remember that?
Something divided by 3.
No. Surface area as a function of radius is, nobody remembers? squared. There you go. 4 pi r squared, okay? So if I know that the surface area S is equal to 4 pi r squared, does anybody see a way that I could merge this information algebraically and come up with a new model? V of S instead of V of R.
Multiply that one.
That's not, what do you mean multiply? No, then my answer is no.
You do something.
When you do something, is correct.
Maybe add it.
No. So what do you notice here? I've got volume as a function of radius, and I've got surface area as a function of the same input variable, radius. Input is that word is going to be maybe important at some point, so there's get a very small amount of partial variable.
Very small.
Very small amount.
I think you can plug it in there.
What do you think? Any ideas?
I got plenty of ideas.
Plenty of ideas. Okay, so this is a really good technique, really good trick that we use in algebra. We can make what's called a substitution equation, right? So now think about this. If surface is a function of radius and volume is a function of radius, what if I solved this equation, S equals 4 pi r squared? What if I solved that for R, right? What am I really doing here? The way it's written right now, S has been isolated, and so this is the formula we might say we're going to use to calculate S if we're given R, right? But I could always do this, right? I could always say, oh, I guess that's my answer. I don't want to go there yet. Oh, that's right. Seems bright after being on the other pages, doesn't it? Okay, let me- Yeah, that's better. Okay, so we started off with V equals 4/3 pi r cubed, and S equals 4 pi r squared. Well, what if we want to solve for R? Okay, we're not used to doing that. We're used to solving for a single, you did this a little bit during the review section, right, at the beginning of the year. What if I want to solve for R, isolate R in terms of S? What are the steps I would go through to isolate R? Divide by, well, and then divide by 4 pi. Okay. So if we divide each side through by 4 pi, I can cancel vertically there, right? So I end up with R squared equals S over 4 pi. What's the last step? Square root, right? So I get, if I square root, what do I get? Plus or minus the square root of S over 4 pi. Okay, but let's think about this now. Radius is not just, radius means something geometrically, right? Does it make physical or geometrical sense to have a negative radius? No. It doesn't, right? So we can say, well, we realize here, because this is a geometric problem, we can't have the negative solution, we can just abandon, right? We can dismiss that one, only take the positive one. And so if we simplify this, if I square root a fraction, that's the same thing as just square rooting the top and square rooting the bottom separately, right? So we get R equals the square root of S, that's supposed to be an S, over the square root of 4 pi. Well, what can I do on the bottom? So I can take the 2 out, and I just end up with the square root of pi, right? But no tens in the basement, so what do I need to do? Okay, good. So you know what though, we'll get there. Maybe let's not even worry about that for now, because that's not going to be our final answer. We could, but let's just leave it like that for now.
Is there any point with the circle with the negative radius, but it wouldn't work in a math problem?
No, it works, things can work mathematically, but not physically, right? So that's one that just doesn't work physically, okay? So we've got a formula for R now, right? We got the formula, R equals 1/2 times the square root of S over pi, something like that, right? Or I could just leave it as square root of s over 2 times the square root of pi. Either way, doesn't matter. I've got this formula for r. Notice that r is now a function of s, right? So what would happen if I substituted this r into that equation? I don't want specifics, but what's my answer going to look like then? I'm going to get a bunch of numbers, but what's going to be my variable? It's going to be like s, right? So that's, we could call this a substitution equation. The variable that we're wanting to get rid of, we want to substitute for, which is r, right? We want to end up with s's instead. All we have to do is isolate that variable, solve for that variable, and substitute, right? Look what we get if we do that. So then we end up with v equals 4/3 times pi times r squared. But there's my r, right? So let's just make this, write that in yellow so we can kind of follow its progress here. We end up with that thing. Cubed. That's just r, isn't it? This just says 4/3 pi r cubed. So what would I have to do now?
So they do that for r radical
So I know we haven't spent a lot of time, we haven't really talked a lot about like rational exponents and things. So instead of writing this using powers, if I cube something, what am I doing when I cube something? Multiplying it by itself 3 times, right? So we could rewrite this without using any fancy math that we haven't talked about. We could just write it this way. 4/3 pi times, well, I could distribute the 3. One thing I could do is distribute it to the 1/2 and then distribute it to the square root, right? So what is 1/2 cubed? 1/8. So let's just put the 8 on the bottom right there, right? We can do that. And then all we have left is this part. So I've got the square root of 5 over pi. Let's just make that the square root of 5 over the square root of pi
Wait, isn't it s?
times the square root of 5. Oh, you're right. I can't read my own writing, can't I? Square root of s over square root of pi times square root of s over square root of pi. In other words, the square root of s cubed over the square root of pi cubed, right? So that gives us on the top what? So here I've got my 4 pi over 24, or yeah, 24 times square root of s times square root of s times square root of s. So what does that give me? Square root of s times square root of s is s. Okay. What about the bottom? I get square root of pi times square root of pi is pi times square root of pi. So some stuff cancels then, right? Look, I end up with those pi's cancel, right? 4 over 24 reduces to 1 over 6, so it's starting to look better. So that leaves us with s times the square root of s over 6 times the square root of pi. Well, we're almost there. What's the only problem we have left with this answer? Yeah, I can't have a 10 in the basement. So what do I have to do?
Times by radical pi.
Good. And then that gives us a pi on the bottom, right? So we end up with now s times the square root of s times the square root of pi,
Yeah.
right? So we could even put that inside there if we wanted. All over 6 pi. Okay? And that's fine. So the answer I gave you was that, right? That we just didn't simplify that. And what did we do there? Really, I forgot what I did. This is just the part where, that's the point where, right there, right? That's just where we make the direct evaluation. And then we simplified this whole thing down to our final answer. Look what we get. We get volume as a function of surface area is that, right? S times the square root of S pi over 6 pi. So it's kind of a complicated looking function, but really, so's that. That's kind of complicated looking too, really, right? This one looks a little more complicated, I agree, but it's useful. I mean, we might, in some weird situation, maybe we're given the surface area of a sphere, and we want to be able to directly calculate the volume. Well, that function we just derived does that for us. I can input a surface area and just, plug in values for S into our answer. It's going to give me back a volume, right? Okay. Go. I'm done. 1 minute? Oh, I guess I did take more time than I thought. First time ever.
You're like.